a bit disclaimer, the video is going to be a bit long because we will actually learn all the concepts starting from math, inclusion, exclusion. We will search, like we'll learn about binary search, we'll learn about bit masking, we'll learn about the masking concepts also. And if this is the first time in our channel, so we after every contest we discuss all the problems of the contest, and you can see the links and all that stuff. You can just write the problem name by Aryan Mittal, you get the video. Now the problem simply says that again, it's a very good problem. It simply says that we are given, again not simply, it says that we are given an integer array called as coins, which represents the coins of different denomination. So if I am saying that I have some coins array, so it just represents some coins with a different denomination, which means, okay, a coin of denomination 3, which means that, let's say, how we have, let's say, 10 rupees, 5 rupees, same way it is a denomination of a coin. Now the strange and the biggest fact is that the denomination, or basically the coins, are distinct. I will never see another 3 occurring here again, ever. I will never see that. That's also a good point. Remember all these points, it will be very, very, very beneficial. You have infinite number of coins of each denomination. If I ask you if I have denomination of 3, so I have infinite coins of 3 denomination, so which means I can do anything with those. And basically I have to return the kth smallest amount that can be made using these coins. What we mean by that, we will see with the example statement itself. Okay, we have 3 denominations, 6, 3, 6 and 9. For 3, if I choose a denomination of 3, I know I have infinite coins of 3. I can make a value of 3, I can make a value of 6, I can make a value of 9, I can make a value of 12. Which means, okay, how I will make a 9? I will take 3 coins of 3 denominations. Same way, if I have a 6, a coin of denomination 6, I can make a value 6, 12, 18, 24 and so on and so forth. Again, so on and so forth up to infinity I can make, because I have infinite coins. Same way for 9, I can take 9, 18 and so on and so forth. Now, if I just club all these coins whatsoever I have got, again, these can be infinite coins, infinite coins. If I club all these coins together, I will realize that, okay, I will have a sequence like this. I will have a 3, I will have a value of 3, I will have a value of 6, value of 9, value of 12, value of 15 and so on and so forth. I want the third, again, third smallest amount. For me, if I look at the sequence which I have generated, the third smallest amount for me will be a value of 9. So for me, again, just make sure how I term these stuff. I have termed it as x. So remember that, okay, because it will be helpful. Although right now there is no meaning of x, but still make sure that you understand what I have named stuff. That would be very helpful. So I am saying, okay, my third element in this sequence, basically the kth element in the sequence, is 9. That is my answer, and I have named my answer as x. Okay, same way, if I take the next example, 5, if I have, I can have infinite values, which means 5, 10, 15, 20 and so on and so forth. Same way for 2, 2, 4, 6 and so on and so forth. If I club these denominations, I will get a 2, 4, 5, 6, 8, 10, 12 and so on and so forth. My x as 12, which means what is the 7th occurrence in this entire sequence, will be a 12, which is my x. Now, the one very basic fact which might come to your mind is, why don't I generate this sequence and then I will just club the sequence and I will generate the kth element? Bro, if you even plan to generate the sequence, and if you want to, again, you will say what is the length of this sequence. For sure, the length of this sequence you will try to generate as minimum as possible. If you try to generate the length as minimum as possible, still, to have the kth element, your length should be your length should be k, to have the kth element in the sequence. So I'm saying I will generate a sequence of length k. Let's have a look at the k. K is 2 into 1e9. You cannot generate a sequence of length k. So things are sorted right now that I cannot generate a sequence of length k. What else can I do? Let's see what else can we do. So right now I just realized a few things, that I had many elements in my coins, and then from those elements, for each of the element I was generating a sequence and then clubbing that sequences up and to get my kth element. Now let's not confuse it. Let's make the problem a bit small. Let's separate the problem, because here you were clubbing the sequences, right? You get the sequence of 5, 2 and then you were clubbing it up. I'll say, what if you had only 2? You had only one element, which is 2. So you know that you don't need to club any sequence. You will just generate a sequence of 2, and then from the sequence of 2 you will find the kth element. So let's say if I just plan to generate the sequence of 2, which means 2, 4, 6, 8, 10, 12 and so on and so forth. I am asking for the 6th element. Again, remember, right now I have only one element in the sequence, and then I will progressively increase the number of elements which I want and I have. So let's imagine that I want my sixth element in the sequence. So first very basic doubt will be, Aryan, how to even think of what element to get? Imagine that you have some k. Aryan, mathematically, I'm thinking of a formula that if I want, let's say, the sixth element of sequence, maybe I might end up dividing by something, like maybe by 2. Let's say if I have some sequence, I want the sixth element, so I know 2, I will multiply by 6, I'll get the number 12. Okay, that's one way to get, but where, like, how will you go about for the other part of the problem? You might not, because you have a k. Again, we have an idea, we are breaking it down, but we also are correlating with the existing problem, and we are thinking of the future. Okay, we have to relate back to the other values also. So right now I have only one value, I have my k. If, again, my k is very large, so that's one also a hint. My k is very large, so maybe I can apply binary search. That's a big hint for me, that maybe, because see, whenever your answer range, or basically your range in which you have to search, because it is, what you are doing, you are searching for the kth element, and your search space is itself very large, so maybe you can apply binary search on the search space itself. So that's one thing which we might end up using. So if we even think about in that direction, so how will I perform the same thing? Why? By thinking of binary search. Again, I just thought of as a hint, I will try that hint. If it works out, good. If not, then I will try for something else. Then I thought of maybe, okay, seems good, that what and how will binary search work here? So let's imagine I have all the sequence of numbers. Again, for me, the only visible numbers are from 1 to, let's say, 1e9, because that is the value, that is the visible value for me. Or maybe, let's say, my 2 into 1e9. So if I ask you the kth element in this sequence, then you will land, again, how binary search works is that we land onto any location, and then we check if that location is good or not. If it is good, then we go maybe left or right, depending upon wherever we think of, we will find a good location. So randomly, let's say, again, maqsad nahi bolna, our main aim was to get the sixth element. I know this is the entire sequence of numbers which I could have from 1 to up till 1e9. Let's say right now I put 1e9, but okay. Then I went on and tried the possible value. Again, remember, this is the possible value of x, your answer, because this 8 is a possible value of x. That's the reason I just put in the x here, so as to make sure that this is a possible value of x. So then, possible value of x. To make sure that this is your k or this is not your k, you will have to know what is the occurrence of this x. You will check, okay, the occurrence of this x will basically, okay, you have 8, you want the multiple of 2. So you will do a 8 by 2, which is 4. So as you can see, 2, 4, 6, 8. So 8 is the fourth occurrence. So I can easily see that this x is the fourth occurrence. And I can also see it is 2, 4, 6, 8. What it also mean is that count of elements which is less than equal to 8, which is the multiple of 2, are 4. Right? Then what I was looking for? I was looking for my sixth occurrence. I got to realize this is my fourth occurrence. So my higher occurrence will be found on the later half of my sequence. So I realized that I have to discard the previous sequence, and I will have to go for the later sequence part. If I have to go on the later sequence part, I know that I have to jump my mid. Again, this is imagining a binary search. So I will discard the entire left portion. I'm doing a binary search on my entire sequence range. And thus I will jump onto my right, which means I'll do a mid plus 1 to get my required thing. If I do a mid plus 1, which means I'm looking for a higher value of x in the binary search. So right now, you got the basic structure of how the binary search would look like. But still, for a basic binary search naive, you need to know the L and the R. And you realize that this R is actually the range X. And I realize this thing which I've put in right now in this location, it is a value of K and not X. So the issue is, what will be the value of X, which means what is the value of R in this entire range of sequence of numbers. Now for this, I will ask you, what is the limits that will define your value of R, which means you have to find, let's say you have to find the third element, right? And that you realize it could have been 9. If you go back and you look that here the x equal to 9, and this is the third element. Again, third was your K, and this was your x. So you obviously realize that your x can be higher than your k. Third element, value is 9. So I realize that I have to get the value of x itself. Here, I'll take the maximum stuff, which means I want to find, let's say, 1e9th element, and for sure I will take the maximum thing, which means 25. 25 is the maximum number. So what will be the 1e9th element if I start from 25? So what I'll do, again, 25, next number will be 50, next 75, and so on and so forth. And I want to have 2 into 1e9 numbers. Again, this is 2 into 1e9 numbers because my k is 2 into 1e9. So I can have, I might ask you, what is the 2 into 1e9th element? So you will realize that this is nothing but a simple AP. And you have to find the nth element of an AP. If you have to find the nth element of an AP, so that element will be a plus n minus 1d. A is 25, n minus 1 is 2 into 1e9 minus 1. Imagine that. Imagine it's the same as 2 into 1e9 into 25. So your nth element will be 25 plus 2, like 2 into 25 into 1e9. That will be your value of your R. Now, to just have an upper bound, just to not put in just a big value like this, you can also put in a higher value, let's say 51 into 1e9, or you can also put in 100 into 1e9. That also will completely work. But this, below this, if you will go, below this an value, if you go, you will start getting wrong answer. So that's how you realize that, okay, how will I get my R? So now my LNR is done, my binary search is done. Maybe this way I can do it for just one number. So I realized that how my code will look like. Again, so far we have just imagined I have only one number. It can or cannot go wrong. So far we realized, okay, my L will be this, my R will be the same value I proved before also. Then a simple binary search template which we have been following every time. If you have not known this template, you can just write binary search by Aryan Mittal, you get a playlist. Just watch this playlist. Now in this we go to my mid. Again, this will not overflow because everything is in the LL, long. Right now, then you will find the count of elements less than equal to x. If you remembered what I was doing, I was getting at a mid x. This is my mid x. This is my mid x. I was finding the count of elements less than equal to x, which is 4. If this count is less, then what I require is I want the k. I want this k. So if this count is less than k, simply you have to move on the right side. If this count is less than equal to k, sorry, if this count is more than equal to k, then move on the left side. So move on the left side. And for sure, if the count becomes equal to k, then you have to put in as answer equal to mid x. Because this is the mid what you wanted. Remember, this is the x. Again, this is the x, mid x what you wanted. Now, for you, many of you might have, again, I'll highly recommend go and try by yourself. But for many of you, you might actually end up thinking, Aryan, why you did not write this same stuff as that if your count is less than x, then do a L equals to mid plus 1. If your count is more than x, then do a R equal to mid minus 1. Else, you can just get your answer as mid x and then simply break. Why you did not do this? I did not do this because if you just look back at the sequence again, if you look back at this sequence, if your mid x lies here, then count of elements which is less than equal to your mid x and also divisible by 2 will still be 6. And with this fact, you will break right here. Which is not true. Because you should ideally try to shrink as much as possible, and then at this point you will actually get the count and you'll actually get the number x. Because remember, this number x is not divisible by 2. It is not divisible by your nums of I. So this value would have been wrong. So you will have to keep on shifting until you get the lowest value, which was actually divisible by your nums of I. So it's the reason I will keep on shrinking. Provided, even if I got my answer, I will still keep on shrinking because this will give me the lowest value, which is actually divisible by that number. Now, this brings your simple binary search considering you have only one value. Although it might seem like, okay, RA for one value, I could have just easily done a math operation, which is O of 1 operation, and you are doing a O of log K operation. It might feel like, but we just did for one value. But now the root issue was for us that we can have many values. And the bigger issue in that is that these values can be overlapping also. What I mean by that is, if you would have gone by your math example, then again, your math strategy and not your binary search strategy, what you would have done is, okay, you would have got the count of 3. Again, remember, by the above strategy, you have only one element, which is 3, or 6 or 9. But now if I go and look at the entire column, I have all the elements, and that elements can have multiple switches overlapping. So if I had gone and I would have asked the count of 3, you would have said, okay, it's 4, because let's say I have my x as 12, which means my x is 12, and I ask you how many numbers are less than equal to 12, you would have given me 4 as an answer, which is you will say 3, 6, 9 and 12. If I ask you the same for 6, okay, what is the count of 6? Which means the number of elements less than your x. Again, remember why I'm taking x as a strategy, x as a point, x as a focus, because I am searching on this x itself. I'm doing a mid x, remember mid x, which is L plus R by 2. So that x itself is my search value which I'm trying to search for. And my condition, search condition is k. Count should be less than equal to k, less than k, or count is more than equal to k. Now, coming on back, if your element, if your count 6 is, which means number of elements which is less than equal to your 12, and a multiple of 6 will be a simple 2. X by number, and it is 1. So representing the same numbers right here also. But if I would actually have asked you that you have to find the count of numbers which is less than your number, this x, which is 12 in this case, you cannot simply add all of them, which means you cannot simply say the count of numbers which are actually less than your number 12 and having all these combinations are actually not 7. Why? Because you can simply see it is 3, 6, 9 and 12. It is just 4 numbers. So actual answer is 4. Actual count is 4. So, okay. In the above strategy, your main thing is getting this count correct. Your main thing was getting this count correct. Ideally, you have to get this count correct, and if you get this count correct, you will simply can apply binary search. And I realized my bottleneck itself is I'm getting my count incorrect. My count, I need to get it correct. How to get this correct? What is actually happening that it needs to be correct? Now, before this, if you have been liking it, if you have got the intuition so far, please, can you please like it? Again, I have written this because I forget in the between to tell, and people like, I know, okay, it's you have to skip it. You can just skip it. But I've seen like even after trying so hard, like we are not getting engagement at all, and it's a bit demotivating. So yeah, please, that will be very helpful. Cool. Now coming on back. भीख लगी ना मुझे भी लगी cool, no worries. So we realized that what was happening was count 3, count 6, count 9. Now I was adding 4, 2 and 1. Ultimately when I was adding 4, I was saying 3, 6, 9, 12 are the occurrences. First count of 6 as 2, it was saying 6 and 12 are the occurrences, and count of 9 saying 1. Okay, 9 as the occurrences. And if I see, then 6 is repeating, 12 is repeating, and 9 is repeating. Oh, I have some repeating characters, like repeating numbers also. So I have to remove those repeating numbers. Do you see that you are taking the contribution of everything, and then something is repeating, then you remove this repeating thing? Did you remember something like that of this sort? Which means you are taking contribution of everything. Now something is repeating again. You remove its contribution. Remember? Yeah, it is inclusion-exclusion. So I'll take a bigger diagram rather than just 2 sets. I'll take a bigger diagram, just saying, representing the same thing as I had number 3, 6 and 9. So I took the contribution of 3. Let's change the color. I took the contribution of 3, contribution of 6 and contribution of 9. Ideally, as you can simply see, contribution of 3 would have been x by your 3, right? Contribution of 6 would have been x by your 6. And again, remember, x in this case, for example, we are taking 12. So I'm also saying 12 by 3, which is saying all these elements are less than or equal to 12 and having a multiple of 3. Same way. But here I will have to remove which is common, and that is where this comes in, that you remove A intersection B. And again, I'll show you a pattern also, because you must be having some doubts regarding it. But yeah, no worries, you will see many stuff. Now you will remove the contribution. What is A intersection B? Okay, you will remove the contribution where 3 and 6 both will come as a multiple. Now what that can be? That can be 6, that can be 12. Aryan, why that was not a 3? Because bro, 3 was not there. Like again, I did not count it 3, 6, 12 and so on and so forth, because see, 3 is not the number where both 3 and 6 can come. So where both of them will come, I will take that number. I'll take that number, and that's contribution I have to remove. So both 3 and 6 will come at 6. Both 3 and 6 will come at 12. What is that number? What is this number 6? Did you see? What is this number 6? This number 6 is actually the LCM of your 3 and 6. For example, if your number would have been 2 and 5, then your first number having both 2 and 5 will be your LCM of 2 and 5. If your number would have been 2 and 10, your first number having both 2 and 10 will be the LCM of 2 and 10, which is 10. If you had 3 and let's say 6, same. Your first number having both 3 and 6 will be the LCM of 3 and 6, which is 6. So that is how I get the first number having both 3 and 6, which is in this case for us is a 6. Again, to show you. And thus I can simply say I have to go up to 12. So I can have 6, 12, 18 and so on and so forth. But my limit was up till 18 itself. So I realized that right now my LCM of 3 and 6 was 6. And earlier I was doing a x by 6. To know the count of elements having a multiple of 6 and less than equal to x. Now I will do a x by LCM of 3 and 6 to know the count of elements less than equal to 6 having a multiple of both 3 and 6. For both 3 and 6, I am taking a LCM of 6, LCM of 3 and 6. And that is how I can simply get this as, okay, x by 6, which is x by, which is 12 by 6, which is 2. And same way, I try to do it for 6 and 9, but 6 and 9 LCM is 18. So if I do a 12 by 18, it will be a 0 because the first number which is having both 6 and 9 will be a 18. And that 18 is more than 12, so I don't need it. And same way I did for 3 and 9. And the same way, if you had remembered a Venn diagram, a simple inclusion exclusion, it also adds stuff. Depending upon, I'll show you in the entire sequence how things are added, but that's a pattern of how it follows of inclusion exclusion. So you are doing what you are doing. Okay, now you realize that, okay, you have to use inclusion exclusion. Then you have to also get the LCM of this entire group of AB, AC, BC, ANC. You have to get the LCM of the entire group. So firstly, let's see how these groups are made. And then we will see how to get the LCM of these groups. Again, LCM is a simple function, which is simple. LCM of two numbers, A and B, is LCM of A and B. It's a function itself in C++. If you even don't know, then if you must have for sure remember underscore GCD of A and B. That's also a function. So if you know this function of GCD, you can simply say A multiplied by B upon underscore GCD of A and B. Because it's a proof that GCD of two numbers multiplied by LCM of two numbers is actually the multiplication of those two numbers. Cool. Now coming on back, that we still had an issue, Aryan, how, okay, this is for the 3 numbers, but how it will look like for 4 numbers, 5 numbers and n numbers in general, because I know I have n numbers. Now if I have, let's say, 3 numbers, I realize that I will take the contribution of each of them individually, then subtract the contribution when they are in double, then add the contribution when they are in triple. Okay, what if I had only 2 numbers? Then I will add the contribution when they are single and subtract the contribution when they are double, because I hate double. I hate couple. Oh, sorry. So I will simply have a ABC. Again, let's take the 4 elements. I will add the contribution of the single because I love single. I'll subtract the contribution of double because I hate double. And then I will add the contribution of 3 because I like 3. And then I will subtract the contribution of 4. Right. So you will see, okay, it's a pattern. For 1, you are adding. Again, for 1, you are adding. For 2, you are subtracting. For 3, you are adding. For 4, you are again subtracting. So it is okay. For odd count, you are adding. For even count, you are subtracting. So in a group, when I have even numbers, I am subtracting its contribution as in the count. And for a group, again, how we will make this group, how we will make all the stuff, you will see. But what we are doing is, okay, if the group has an even count, I will subtract it. Odd count, I will add it. Now, the issue is how I will make this group. Now, whenever you have to try for all the possible values, as you can see, if I take this as an entire set, which means if I take A, B, C, D, what I am doing, I am trying, okay, once A, let's say once AB, again, once BD. So I'm trying for all the possible combinations. So in these cases, for sure, remember, when you have tried for all the possible combinations, you must have remembered a term called a subset. To generate subsets, you have to, or you should use, again, you can also do it by other ways also, but the most easiest and the most intuitive way is by bit masking. What and how it is done? If you know that you have 3 numbers, your size of array is 3. You have to generate all possible combinations with these 3 numbers, which means you have to generate all possible subsets. Then what you have to do is you have to make a mask. Mask having, okay, all of these occurrences as 1. This is a mask. This is the highest mask which I will make. Mask is nothing but a pattern, right? A pattern which says, okay, this is what I will try for sure in future. So I will, again, how this mask is made of 1, 1, 1, simply saying if I have n occurrences, or say m occurrences of these elements, which means I have m occurrences in the entire array of numbers, I have m elements, I will say 2 to the power m minus 1. Or for the more advanced people, they say 1 left shift m minus 1, saying I left shift my 1 m times, so I will have m zeros, and then if I do a minus 1, I will get m ones. So you can simply see I will have m ones as a bit represented as a binary form. So if I have, okay, from 1 to I have m ones, I have m ones. So if I go on from 1 to your m ones, which is number 7, you will actually see, you will get all the possible occurrences. Same way, I went from 1 to number 7, I got, okay, 1 1 0 1 1 1 0 0, so on and so forth. So this 1, I can map it to my second element. Again, if I represent this array 3 6 9, so let's say 3 6 9, or let's say a b c. So if I map it 0 0 1 0 0 1, so you see, I will simply say that this is the index, and I am taking this specific index. Wherever there is a 1, I will take that specific index. Okay, 0 1 0 0 1 0, I'll take this specific index. Okay, same way, 0 1 1 0 1 1, I'll take these both indexes, which means b and c. So I'm taking b, b c, and so on and so forth. And I know that how I will get this for sure. If I have only one element, which means the count of elements which I've taken is 1, or to be more precise, I'll add the contribution in my count as a, because remember, मकसद नहीं बोलना, our main aim was to get this count. If you remembered, the main aim was to get this count. If you get this count, you're sorted, and you have to get this count by taking the contribution of everyone, 3 6 and 9. So you realize the contribution of everyone will be 3 6 9 3 6 3 9 6 9, and last 3 6 9. So that's how you will simply get it. Make sure, right? Now coming on back, we realized that we will just simply get all these individually. I'll simply add the contribution. Again, for adding the contribution will be count plus is equals to what? X upon LCM of this specific thing. It can be either C, can be B, can be BC. So I have to take the LCM of B and C to get this LCM in bottom, to add its contribution in the count. All right, and thus I will be getting my count, which will be, again, count for this specific one thing. I have to go and try for everything to get the actual count of all the possible pairs, to ultimately apply inclusion-exclusion principle and do addition and subtraction. How I will do again addition for 1 as an odd frequency element, as an odd number of elements, and even for, like, if I'll do a subtraction, and thus I will get my individual count. I will add its contribution or subtract its contribution, and then can simply get my answer. Cool. Thus you will get the count. You know how to apply bind search. You will simply get your answer. Now, code, it's not pretty simple because we applied 3-4 concepts: bit manipulation, bit masking, your AP formula, which means your simple maths. We applied binary search and also the entire intuition of the solve. Cool. Now, what I will do, as I've showed you previously also, I will have a L and I will have a R. Remembered, in this R complex form, you can also, again, this is the minimum R you have to keep. You can also keep your R as saying, okay, 1e9, like 1e11, which is 100 into 1e9. You can take 1e11 also. That also will completely fine work. Any higher value, 1e18 will also work. Now you will actually apply simple binary search. You will find a mid X, which is L plus R by 2. Again, both L and R are integers. That's the reason it worked. Sorry, both L and R are log norms, so it's a reason it worked. If it would have been your integer, so apply your L plus R minus L by 2, that formula. Now you will get the count. You will get the count. Count less than or equal to your X. I will pass in my coins array. I will pass in my current mid X, and I will check what is the count. Then this count, again, I will show you what is the count. But again, if this count is less than X, then try for a right side. If this count is more than X, if this count is more than equal to X, then try for the left side. And again, even if it is equal to X, then still go and try for the left side, because you want to actually find which is the multiple of that number, not more than multiple of that number, right? So it's the reason I explained it previously also, why you have to keep on doing it, so as to make sure your number is exactly the multiple. Now you can simply get the answer. Now, if I show you the function, which is count less than equal to X, it's simply, firstly, I will actually make a mask of all ones of M ones. If you remember, see, this is the mid X. Okay, yeah, this is the mid X, which saying I need to have all these number of ones. Why I put a mid X here? Cool, no worries. This is actually your M. I don't know why I put a mid X here. It should be your M, but yeah, no worries. So this is your actually mid X, right? Now, this is your M. This is your M. So what you will do, you will make a mask of all your M ones. Now, when you have your all M ones, you have to get the count. That is a count. Now, what you will do, you have to try again. This is your M elements. You have to get your X, right? So you will try for all the possible combinations from 1 to your all ones of M, and I showed you all the possible combinations. Now in all the possible combinations, you have to realize that for every of your individual pair, which means for every of these, if I go back, okay, for C, again, you are trying for all the possibilities here. What is what you are trying for all of them. You have to either add its contribution or subtract its contribution. But before doing anything, you have to get its what? You have to get its LCM, right? For every of this mask, individual resultant mask, you have to get its LCM also. So okay, for one specific mask, I am trying to get the LCM, an LCM of set bits. This set bits represent that, okay, that corresponding bits are set, which means, let's say if the mask is of ABC, but only B and C are set, so I will get the LCM of B and C only. So how I will get that? I will iterate on my entire coins array. This is my coins array. I should have this as M because this I named it as M. I will go on to my entire coins array. In my coins array, I will just simply go and ask if that corresponding mask is set, and I will just check, okay, for that specific index, let's say index is 1. If the index 1 is, and when I say index 1, I mean, okay, there's index 0, 1, 2, 3, 4. This is the indexing in your coins array. To check the contribution of 0, I will check the mask. And in my mask, the first element, again, it's 0th bit, again, it is a 0th bit, first bit, second bit, third bit, so on and so forth. So as to check, okay, is the first element, do I have to take the first element in coins? Do I have to take it? I will check, is my mask there? Which means 1 is the element, left shift 1 will give me, again, this left shift is for I. This left shift, again, this is the index I. So I'll do a 1 left shift I to actually go on to that specific value. If in the mask it is set, so I have to take the contribution of that specific index I. So in my mask, if I erase this, in my mask, if the J is set, I will take the LCM of J in my entire LCM result of that specific mask. And then I told you, if the count of bits, or basically the count of elements which I've taken in that specific mask is odd, I will add the contribution. If it is even, I will subtract the contribution. And again, to know if the count of elements are odd or not, so in the mask whatsoever I have got, I'll ask the number of set bits. If the count of the set bits is odd, which means I have odd number of elements in the mask, so I will add the contribution. Contribution is nothing but X upon the LCM of that specific mask. And if it is even, again, X upon LCM of that specific mask, do a subtraction, and ultimately getting the count. And for sure, I will keep on doing it, and ultimately I can simply get my answer as a result. So you realized that you will be making 2 raised to the power n. You will make 2 raised to the power n possible combinations, and that is itself here. You are trying for all 2 raised to the power n possible combinations. You are trying here itself. This will take O of n time. So it is O of, this is O of 2 raised to the power n. This is O of n. Right? And same way, this will actually go for O of log k time, and this one thing will actually take O of 2 raised to the power n into n time. So my time complexity will be O of n into 2 raised to the power n multiplied by log k. Space for sure 2 raised to the power n because I am using a mask. Cool. I hope you got it. It's a very good question involving maths, binary search, bit manipulation. Three most fearful concepts of programming. Bye-bye. Take care. Again, if you liked it, please do check the comment section for one video which you should watch. Again, I have not mentioned it, but you should watch that if you are in college. If not, then you can skip that video, but I highly recommend to watch the video if you are in college. Bye-bye. Take care.